Hello again, everyone. Welcome to our discussion of section 4.1, where we will be talking about polynomials and their graphs. A lot of mathematical functions are categorized as polynomials. They have many uses in modeling data, real-world data. So it's important to know what kinds of functions they are and some of their features because they are used in the real world a great deal. Before that, I'd like to remind you that to please read through or skim through section 4.1. Some spend about half an hour to 45 minutes. Just read through it, and before you watch the video or before you attend the class. Then watch this video, attend class, and take careful notes about the things you see or hear that might be important to you, and also make note of any questions you might have. Next, you would want to revisit the textbook section that you read, and this time answer those questions that are solved in the book without looking at those solutions, and watch the video again, and without looking at the solutions that I give, write down your own answer. Preferably, as you watch the video for the first time even, always pause the video when I get to an example problem, solve it on your own paper before you watch me go through the solution set. This is the fastest, most efficient, and most effective way of learning mathematics, that you get involved and you solve these problems before you see somebody else working them out. It's critical. Like I've said this several times before, it does not matter at all that your solution could be incorrect. That's not even relevant. What's relevant is that you are getting your brain involved in these kinds of mathematical calculations. That's the most important thing. Okay, so of course, and after you've done this exercise by watching the video and reading through the textbook, then please complete all the homework assignments by the due date. And of course, because mathematics is always cumulative, you would want to visit or revisit the previous material. I'd say half an hour a week. If you spend 30 minutes a week refreshing your mind each week by going over the previous sections, then that will be great. That will help keep all the material fresh in your mind as we move further into the upcoming sections, because all these sections make use of some or all of the previous skills that we've learned in this and even other classes. Okay, so here are polynomials. This is what they look. I mean, you're not expected to remember this from memory, but I think it helps to get a feel for what polynomials look like. So in this case, what should catch your attention is that the first term is some x term to some power. Okay, and then and in a polynomial, we would like to order the terms in the descending order of powers of x. And x, of course, is just one independent variable. You might choose other independent variables, say k, or l, or m, or p. It doesn't matter. So it's some independent variable to some power, and it has a coefficient. When we order the terms in the descending order of power, that's when you see x to n power, x to n minus 1 power, x to n minus 2 power, and so on and so forth. So these n and n minus 1 and minus 2 are looking at the descending orders of power. That's all it means. And then these coefficients that are termed a sub n minus 1, they're just saying, it's just indicating the coefficient of the x term that has this power, n minus 1. Coefficient of the x term that has n minus 2. This is just a fancy way of, or a mathematical way of referring to the coefficient of each term. That's all. And as you see, the last term is just a constant. A naught is a constant, or could be a constant. Because even though polynomials have these terms that are like this, it's not guaranteed that we always have a constant. We might have just a constant, and all these terms could be missing. It's okay. It's still a polynomial. The other thing important about polynomials is the terminology used with these terms. The polynomial term with the highest power of x, it's called the leading term. So that is called the leading term. And let me actually write down an example of a typical polynomial. So p of x, let's say 4x to the fifth minus 2x cubed plus 7x squared minus, and let's say minus 9, right? That's a polynomial. So the leading term in this example of a polynomial is the term with an x variable with the highest power. And like I say, this x can be any variable. It could be z or w. But as long as it's an independent variable to some power, the leading term is the term with the highest power. So in this case, 4x to the fifth, all of that is the leading term. Now, the coefficient of the leading term, that is 4, is the leading coefficient. And we have examples that we will go over. Okay? Then n, or the highest power that appears in the polynomial, the highest power, n, is called the degree of the polynomial. Okay? So in this example, the leading term is equal to 4x to the fifth. Okay? The leading coefficient is equal to 4. The degree of the polynomial is 5, the highest power. All of these have a significance, and we will look at that in a bit, in a few minutes. The exponents in a polynomial can be whole numbers only. As a matter of fact, as I mentioned right underneath it, the exponents cannot be negative or fractions. I mean, if they are, then we do not have a polynomial. That's what we're saying. So these powers must always be positive whole numbers, just like what you see. They cannot be fraction, cannot be negative or fractions. So we cannot have a square root or cube root or fifth root in a polynomial. And if you do, that expression is not a polynomial. So this is basically saying the same thing as above. And let's see what else. Okay, we've talked about that one. A polynomial is always continuous function. This is very, very important. Okay, a polynomial is always a continuous function. At no place the polynomial is ever undefined or has a gap. Okay, let me move this up. These last few points are extremely important. Right there. What you see on the screen is very, very important. A polynomial is always continuous. That means the domain of a polynomial is always negative infinity to infinity. Always. As soon as you have a polynomial, the domain is negative infinity to infinity. You don't need to waste time investigating for which values of x the polynomial is undefined, because there's not going to be any x values for which the polynomial is undefined. So the domain is that. The following graph shows examples of various types of discontinuities. These are all discontinuities. Look at the gap. That gap indicates discontinuity. This hollow circle is a discontinuity. This Look at this asymptotic behavior. That's discontinuity. That hollow circle is discontinuity. Look at that. We have a hollow circle and a gap, a very small gap, but a gap between these 2 points. That's a discontinuity. So what's the point of this graph? It's saying that a polynomial cannot have these. It cannot have gaps. It cannot have discontinuities and gaps as you see this graph has. Okay? So, and that's why the domain is always negative infinity to infinity. And the bottom says, always arrange the terms in a polynomial such that they are in descending order of power. Yes, because that is usually how, or always, the way we represent polynomials. And if they are presented in a way where the terms are not in descending order of power, we will place them in the descending order of power. Okay, we take the time to do it and organize it in that fashion. Okay, so in the next slide, or in the next page, in each of the following cases, we want to determine the leading term and the degree of the polynomial. So take the time. You're seeing all examples on this page, with the exception of the bottom of the page, which is a different type of problem. But now is a very good time for you to pause the video, and given what I discussed in the first few minutes of this video, answer this question. Write down on a piece of paper what is the leading term and what is the degree of the polynomial. Okay? I'm counting on you to do that. So I'm assuming you're finished with that work, and now you've unpaused the video and now you're back. So welcome. So the leading term in this case, notice how the terms are not in descending order of power. So I always take my time to put these terms in the proper order. So with the term with the highest power first, then the next highest power, then that one, and that one. Do you need to do this to answer the question? No. But I like to do it. So now it's the terms are in the proper order. So then the leading term in this case is all of this. So that is the leading term. And they say, and the degree of the polynomial. The degree of the polynomial is equal to equals to 4, right? To the highest power of the polynomial. Then this polynomial. So here, the leading term is -6. It's the only term. And the degree of this polynomial, because there is no x term in it, so the degree must have been 0. So x to 0 power is let's see. So this is leading term, and the degree equals 0. There is 0 degree, right? There is none of the x terms are present here. So the degree is 0. If we did have an x, suppose we had x minus 6, then the degree of the polynomial would be 1. But in the absence of any of the very independent variables, then the degree of the polynomial is 0. Okay. Next one. So the terms are in proper order. That's good. And the leading term is that one. And the degree of the polynomial is, of course, the highest power, 3. Okay, like that. Next, let's put this in order. So we have f of x equals minus x squared plus 2. And the leading term is that one. And the degree of the polynomial is equal to 2, right? 2. That. And this one, so we have f of x equals x plus 12, and the leading term is that one. And the degree is equal to 1, right? 1. Like that. Okay, I hope these answers match what you wrote on your own paper. All right, so the next topic, zeros of a polynomial function. So we've talked about zeros of a function before, right? Those are, zeros of a function are called, have different names. One is zeros of functions. The other one is the x-intercepts. Remember, x-intercepts are zeros of a function. And zeros of a function, including polynomials, is any x value that would make the function equal to 0. Okay? So we've looked at that before. And here it mentions it again, the x-intercepts of the function, any value of x for which polynomial p of x equals 0. It's the same thing. So here, in example or exercise number 2, it says determine whether 2, 3, and -1 are zeros of the polynomial. So once again, it would be good if you pause the video, answer this question. It should not take you more than 5 minutes or at most to answer this, and then come back to the video. Okay? All right, I'm assuming you've done that, and now you're back with your own solutions already written on paper. So to find whether these are zeros of this, we need to evaluate the function at each of these quantities. So function f at 2 is equal to 2 cubed minus 3 times 2 squared, right? I'm evaluating this function at 2. Plus 2 plus 6. So what do we have? We have 2 cubed is 8 times 2 is 16. 2 squared is 4 times minus 3 is minus 12, plus 2 plus 6. So 16 minus 12 is positive 4. Plus 6 is 6. Plus 6 is 12. Right? So we have 12. This is not equal to 0. So no. We can conclude that x equals 2 is not a zero of the polynomial. Okay? Let's test 3. So the function, the polynomial at 3 would be equal to 2 times 3 cubed minus 3 times 3 squared plus 3 plus 6. So 3 squared is 27. 27 times 2, that would be 54, right? But let me double check. So here we are. So 27 times 2, 54. So we have 54 here. 3 squared is 9. 9 times minus 3 is minus 27, plus 3, plus 6, right? Clearly, this isn't equal to 0, because 54 minus 27 is positive 27, plus 3 is 30, plus 6 is 36. So once again, 36 is not equal to 0. So x equals 3 is not a 0 of the polynomial. We have one more number to check, right? The function at -1. So that is equal to 2 times -1 cubed minus 3 times -1 squared plus -1 plus 6. So -1 cubed is -1 times 2 minus 2. -1 squared is positive 1 times -3 is -3. Plus -1 is -1 plus 6. So clearly we have -6, -2, -3, -1 added together, we get -6. Plus 6 is equal to 0. So this one checks out. So x equals 0 is, -1. -1, x equals -1, -1, x equals -1 is a 0 of the polynomial. Okay? All right. So the next very important topic to know about is even multiplicity and odd multiplicity. Before we talk about this subject, let me remind you that all these things, this information, this kind of work comes to us from centuries ago, where there were no computers, where there were no calculators to graph polynomials. So these techniques were developed in light of the absence of technology in order for the mathematicians at that time to be able to have a feel for what these functions look like in a graph format, on a piece of cloth or paper, whatever they had at the time that they were writing on. But for that reason, I think they are very ingenious and they are very useful for someone that doesn't have any access to technology to get a feel for how these mathematical functions behave graphically, that is. Okay, so these are such techniques. So multiplicity basically has to do, before we go over it in detail, I want to say that multiplicity has to do with the power of the zeros of a function. So right now, in this exercise we did a few seconds ago, we learned about what is a zero of a polynomial, right? Now, each of these zeros of a polynomial, for example, -1 in the previous example, may be associated with a power. So -1 to 5th power, -1 to 6th power, or 9th power, or 10th power. That power gives this zero what is called the multiplicity. In other words, how many times that zero can be applied as a factor, that zero of a polynomial can be associated with a factor of a polynomial. Okay, so, and that has important significance when we graph polynomials. So here we go, we have suppose some number c is a zero of a polynomial, right? C, in the previous example, it would be some number like -1, right? Just like the previous example. C is a zero of a polynomial. Then x minus c to k power, with k always greater than or equal to 1, that is, the power must be greater than or equal to 1, is a factor of the polynomial. So let me use my scratch paper here. In the previous polynomial, and let me bring it back. Before we read on, we should make sure that we understand what that is talking about. So in this example that we just did, right, this is the one, right? We figured out that if you replace the x with -1, the polynomial is equal to 0. That means that x, so the c in this case is equal to -1. Okay, that's the c. Then x, what that paragraph on the other page that I was just reading was saying is that if a constant value like -1 is 0 of the polynomial, then x minus c, that would be x minus -1, or x plus 1 is a factor of that polynomial, of this polynomial. So this x plus 1 is a factor of that polynomial. This is very important because it also means that if this is a factor of that polynomial, that means if you divide this polynomial by this factor, you're going to get some expression with no remainder. So the remainder is going to be 0. So you're going to find, you divide this by this factor, you're going to get another factor of this polynomial. This is a very useful method, again, centuries ago, where they didn't have the technologies we have today. So they could figure out the factors of really complicated polynomials. And the factors would tell them where the zeros are, and which means that where the x-intercepts are, right? It would have a lot of useful information for mathematicians. So that's what that paragraph is saying. If you find a value, a constant value that would make the polynomial equal to 0, x minus that value, so in this case x plus 1, is a factor of that polynomial. Okay? Which means if you divide this by that, you get another polynomial with 0 remainder. And I'm saying this now twice because it's coming up. That topic, the long division, synthetic division, those are coming up. Okay? So, and the power, the other topic we looked at was the multiplicity. So multiplicity of this factor is 1. Okay? Because it has this parentheses, this factor has power 1. So if you solve this if you set this equal to 0, x plus 1 equals to 0, then x equals -1, you get that, right? What would make that polynomial equal to 0. But look at the power of x plus 1 is 1. So the multiplicity of this 0, the 0 of the polynomial, I mean, the multiplicity of this 0 of the polynomial, that is 1. And soon enough, we will get to a section where it matters whether this multiplicity or power at an odd number or if it's an even number. Okay, if it's odd number, that means the graph of the polynomial is crossing the x-axis at that point. If this multiplicity or power is even, it means that the graph of the polynomial does not cross the x-axis. It hits it, it connects with it, but then it bounces back to the same side. Since I just mentioned the graph of the polynomials, so what does a graph of a polynomial looks like? We already said that the graph of a polynomial is not going to be like this. It's not going to have gaps like that. It's not going to have discontinuities like that, like that, like that. It's not going to have any of those. So what is it going to look like then? It's going to look like a continuous line, like that, like that. It's going to look like that, with no gaps, no discontinuities of any kind. Okay? All right. So let's go back to what we were talking about. So now it should be clear what we mean by that. So x minus c, now you have a way of associating this with the factor of a polynomial. X minus c to some power k is a factor of the polynomial. Okay? X minus c, that to some power, is a factor of the polynomial. And k, the power, as we said, is the multiplicity of c, the zero of the polynomial. Okay? I'm sure you can see that these worksheets are more than just examples. These also summarize the content of your textbook from each section. So especially the ones that I've boxed are very, very important for you to remember. Okay? So now, if k, that's the multiplicity, that's the power, if that k is odd, some odd number, let's say 3 or 5 or 7, then the graph of the polynomial crosses the x-axis at c comma 0. Remember, c is the 0 of the polynomial, which means it's the x-intercept, right? So the 0 of a polynomial will always have this kind of coordinates for that point. It's always some constant comma 0 because it's the x-intercept, right? So x comma 0 or c comma 0. So the important thing to take away from this piece, this number 1, is that if k is odd, that's the power of the factor. If that is odd, then the polynomial crosses the x-axis at 0 comma 0. If k is even, some number like 2, 4, 6, 8, and so on, if k is even, then the graph of the polynomial touches the x-axis at that, but does not cross it. Instead, the graph becomes tangent to the x-axis and curves back toward the same side. So if the line, so what does that mean? Suppose, let me use this scratch paper. So I'm going to draw a graph, and let me actually do this so you can see that. Suppose we draw a graph of a polynomial, and this is what we have. Suppose we have something like this, that, this, that, and that. Okay? Let's say that's how the polynomial graphs. Then notice at this point, whatever, the polynomial has, let's call it something. Let's call it negative, say, negative 3. Right? And let's call this point, these are all zeros of the polynomial, right? X-intercepts. X-intercepts. These are all polynomials. Let's call that 3, and let's call this 7. So, notice how the polynomial is behaving. It's touching, the graph is touching the x-axis at that point. It is negative 3 is a 0, so it should touch the x-axis at that point. But it doesn't cross the x-axis. It bounced to the same side. If this line would have come from above, it would bounce to that side. The point being, at this point, the graph bounces back to the same side. It doesn't cross the x-axis. So at that point, we know we have a factor x plus 3, right?
because that is the c. So x minus minus 3, x plus 3. So x plus 3, whatever this polynomial, x plus 3 is a factor of it. But we also can tell about the power of this factor is that it must have been even. See, if k is even, then the graph of the polynomial touches the x-axis but does not cross it. So we know this power here could have been 2, could have been 4, could have been 6, 8, 10, whatever. But we don't know that. But what we do know is that that power must be even. Even. That power. Okay? And take a look at this juncture. The polynomial hits the x-axis and crosses it to the other side. So we know that, so this factor would have been x minus 3, right? X minus 3 is the factor of the polynomial at this point. We don't know the power of this factor, but we do know because the graph is crossing the x-axis, this power must have been odd. Some odd value must have been the power of this x minus 3. It could have been x minus 3 cubed. It could have been x minus 3 to the first power. 1 is odd, right? 1 is an odd number. 5, 7, 9, 11. It could be any of those odd powers. And again here, we know that at that point, the polynomial has this factor, x minus 7 is a factor of this polynomial. We don't know what power it must have had, but because, again, the graph hits this x-axis and bounces back to the same side, because the graph does not cross the x-axis, we know this power must have been something even power. 2, 4, 6, 8, any of those numbers. Okay? So that's what this box is talking about. I hope it's clear. Okay? If not, make sure that you let me know with your questions. Okay, so having said that, this one, for each case below, find the zeros of the polynomial and state the multiplicity of each zero. Well, everything is in factored form, so it's really easy to find the zeros of the polynomial, right? And we can easily look at the powers and state the multiplicity of each zero. So at this point, I highly recommend you for A through D to pause the video at this point, answer each one, write down the zero of the polynomial, and state the multiplicity of it. And if you are interested, this question is not asking for it, but if you want to, also write down at that zero whether the graph of the polynomial would cross the x-axis or not. Okay, so let's add that to that. Okay, so go ahead, pause the video, finish that, and then come back to the video after you're done. Okay, I'm assuming you're done that, and now you're back. Okay, so the zeros here, we know that x plus 5, if we set that equal to 0, then x minus 5 is a zero of the polynomial. Okay, so let me just put here zeros of the polynomial. That means the x-intercepts. That's another name for it, x-intercepts. So x equals negative 5 is a zero of the polynomial. That one. That's a zero of the polynomial. Like that. Then they say state the multiplicity. Multiplicity of that is 3. Equals 3. Right? That's the power. And then, like I asked you, do you think the graph of the polynomial crosses the x-axis at this point, at -5, 0, or not? Or will it bounce back? Will it not cross? It's odd multiplicity, so it must cross the x-axis. So crosses the x-axis. Okay, just like what we said. If it's odd, if the power is odd, the graph will cross the x-axis. Okay. Let's look at another 0. So x minus 4 equals 0. Set that factor equal to 0. Then we have x equals 4 is another 0 of the polynomial. What is the multiplicity of this factor? Multiplicity is 1. Right? X minus 4 has power 1. 1. So, and then it crosses the, does it cross the x-axis? It does cross the x-axis, right? Because 1 is odd. So crosses the x-axis. If k is odd, if the power is odd, the polynomial crosses the x-axis at c, 0, at 1, 0, at 3, 0. The graph will cross the x-axis. So, next one, next factor, x plus 1 equals to 0, then x equals -1. That's another 0 of the polynomial, right? What multiplicity does this have? The multiplicity is equal to 2, right? The power. Does it cross the x-axis or not? Look at this box. Does it cross the x-axis if the multiplicity is even? No, right? Does not cross the x-axis. Okay. Is this clear, guys? You're not here as you watch this video, so I hope it's clear. Okay, this one, part B. We'll do the same thing again. Set each factor to 0 and find the 0 of the polynomial. So x plus 1/2 equals 0. Then x equals minus 1/2. So this is the 0 of the polynomial. What is the power of that factor? 1. So multiplicity is equal to 1, right? Does the graph cross the x-axis at that point, at -1/2, 0? Yes, because that's odd multiplicity. Remember all of this because after we're done with this page and the next one actually, we have another exercise on the next page, and then we have a total of 5. After we're done with all of this, I'm going to go to the computer and we're going to look at the graphs of each of these polynomials at these zeros to see exactly if we were right. Okay, so you might want, as I go through this, you might want to write this down, because once I switch to the computer, you don't have access to this page. So by writing this down, you can then corroborate this information with the graphs. Okay, so if you want to write this down on a piece of paper, if you haven't already, that would be good. Okay, so the next factor, x plus 7, let's set that equal to 0. We have x equals -7. That's the 0 of this polynomial. Oh, look at that. We have x plus 7 twice. So this is actually, so this polynomial, let me write it here. I just noticed it. So x plus 1/2 times x plus 7 squared times x plus 5. So that's what we really have. I just noticed that those factors should be combined. Okay, so all right. So what is the multiplicity of this then? Don't look at that because x plus 7 should have been combined. The same factors should be combined. Okay, so that one has multiplicity 2, right? If I hadn't noticed it, I would notice it soon enough, but if I didn't when I was writing this down, I would say multiplicity 1. But no, x plus 7 squared, that's multiplicity 2. So does the graph of the polynomial cross the x-axis or not at this point? It does not, right? 2 is even. Multiplicity of -7 is even. So the graph of the polynomial does not cross the x-axis. What about the next one? X plus 5 is x equals -5. Multiplicity equals, for -5, it's 1, right? The power is 1. 1. So does the graph of the polynomial cross the x-axis? Do we expect that? Yes, we do, right? Because multiplicity is odd, so crosses the x-axis. Okay, next one. I hope these answers match what you have, what you had written down on your own. So this is x squared minus 4 equals 0. X squared equals 4, right? We're solving for that. And x equals 2. Is that answer correct? Is my solution for x correct? It's not correct, right? What is wrong with it? What is wrong with 2? Isn't 2 squared equal to 4? Yes, it is, but also minus 2 squared is equal to 4. So why did I forget to put this? Wanted to make sure that you'll catch that and you'll notice it. X not equal to just 2, but also minus 2. Remember, every time you're solving an equation like this, and you have to take the square root of both sides, if the x value does not represent a distance, like the radius of a circle, like the distance between 2 points of any kind, then you must have 2 answers, plus or minus. Only when you take the square root of some quantity and that quantity represents the distance, you must toss out the -1 and just keep the positive answer. Okay? So those are the zeros of the polynomial, of this polynomial. So we have then, and then we have a second power on the outside. So this would be, let's see, x plus 2, x minus 2, and each one of those is raised to second power. So the zero of a polynomial, let me write it separately. So x equals 2. That's the zero of that polynomial. And because of this power 2 on the outside, it has multiplicity equal to 2. And that's the same thing. This is true for the other one. X equals minus 2. multiplicity equal to 2. Okay. So for both of these, it does not, the graph does not cross the x-axis. Okay. Okay, so here, one of the zeros of this polynomial is x equals 0, right? X equals 0. And that one has multiplicity equals to 2. And so it does not cross the x-axis. Once again, I'm about to run out of space here. I'll try to fit it all in. So x plus 3 equals 0. Then x equals minus 3. And that one has multiplicity 2 again. And we say does not cross. Does not cross x-axis like that. And then we have x minus 4 equals 0, that factor, right? So the 0 of that polynomial at that point is x equals 4. What is the multiplicity? The power is 1, right? Multiplicity is equal to 1. Does the graph of the polynomial cross the x-axis at this point, x equals 4 or 4 comma 0? Yes, it does. Multiplicity is equal to 1, which is odd. So crosses the x-axis. X plus 1 equals 0. X equals negative 1. That's the 0 of the polynomial. What is the multiplicity of that? Multiplicity is equal to 4. Right? Does the graph of the polynomial cross the x-axis at this point? It does not, right? Because the multiplicity is even. Okay. One more example before I go to the computer, and we could look at the graphs of all these polynomials that we wrote all this description about to see whether we were right or not. Okay. So this one is not factored. What would you do? What would you do? You need to know the factors, otherwise you'll have to use another method to figure out where the zeros are, and we haven't discussed that other method yet. And I don't think in this course we won't discuss that. I think in Math 126 we will discuss another way of finding the zeros of a polynomial, but not here. So what do you think? How would you go about finding the zeros of this polynomial? It's not factored like the other ones. Look at this. These are not, these were factored. I mean, this page is now so crowded, but so let me highlight these so they're more visible on the screen. So this polynomial was factored, right? This polynomial was factored. This polynomial was factored. This one was factored. So it was easy to see where the zeros are. What about here? This is not factor. Have we learned anything so far? Have we learned any techniques so far that you could use to factor this polynomial? Do you remember of any technique we've used that would be useful here? Well, remember that we said when you have 4 terms, what factoring method might be useful? Do you remember that method we talked about? When we have 4 terms, in an expression, in this case the expression is a polynomial, try factoring by grouping. Remember that? We learned about this method not too long ago, one of the previous video lessons. So let's group these two. How do we group? We group, I'm looking at these two. These two have the highest powers of x. So I'd like to group those two, and then I'm going to group these two. Okay? Then we're going to factor each group separately. So f of x can be factored as x squared times, what should I have on the inside of the parentheses to multiply by x squared and get 3x cubed, excuse me. I should have 3x, right? 3x times x squared is 3x cubed. Then plus. What should I have here to multiply by x squared and get x squared back? 1, right? So distribute the x squared into this parenthesis. Do you get that? We get that, right? So we're fine. This is okay. This factoring is okay. How about this group? From this group of two terms, what would you factor out? What is the common term in both of these terms? Or common factor in these two terms? Negative 16, right? Negative 16 times. What should I put here to multiply by negative 16 and get negative 48x? 3x, right? Negative 16 times 3x will give us negative 48x. What should I put after this to multiply by negative 16 to get negative 16 back? Should I put negative 1? No. Negative 1 times negative 16 will give us positive 16. We want negative 16. So what should I do? Positive 1. Okay? So far, so good. Are we done? No. So now, a lot of the mathematics is visual. I've mentioned this before. So visually, look at this expression visually. Is there any common term that you can factor out? There sure is, right? 3x plus 1 is a common factor. So let's factor, because in the previous factorization, we factored out x squared and minus 16. So each of these is just one term. But factoring is not limited to just one term. If you have 2 terms that are common, you can factor out both terms. If you have 5 terms that are common to an expression, to multiple terms, you can factor out 5 terms. So in this case, we're going to factor 2 terms. F of x equals, we're going to factor out 3x plus 1 times. I should put something here such that if I multiply it by 3x plus 1, I get x squared times 3x plus 1. So what should I put here? I should put x squared, right? X squared times 3x plus 1, x squared times 3x plus 1. I get that back. So what should I put here to multiply by 3x plus 1 to get minus 16 times 3x plus 1? You guessed it, minus 16. Okay? Are we done? Is this all the factors of the polynomial?
Are we done? What do you think? We're not done, right? Because the first factor is fine, but the second factor is not. We can factor this expression further. Why is that? Well, let me bring back my scratch paper to remind you of a technique we've discussed in the previous videos. See, this second factor, that one, it is perfect square minus another perfect square. Remember that? Do you remember what I'm talking about? X squared minus 16 can be written as x squared minus 4 squared. Why is this important? Well, we do have a special product formula which I've asked you to memorize, one of the three which I've asked you to memorize, which says that if you have x squared minus y squared, so if you have a perfect squared minus another perfect square, then you can factor this out in terms of x plus y times x minus y. That's the case we have here. We have a perfect square minus another perfect square. So we can factor this, so that this, you can rewrite that in this form. Visually looks different, but it's the same thing. But I rewrote it this way so you can see, in fact, we have this case. We have a perfect square minus another perfect square. So therefore, we can factorize this into x plus 4, like that, times x minus 4, like that. Except in our case, y is plus 4, y is 4, basically. Okay? So this second factor can be factorized more into that, using this special product formula, which I've asked you to memorize. Okay, so let's write it down. So then f of x is equal to 3x plus 1 times x plus 4 times x minus 4. Okay, so finally we have arrived at using factoring by grouping, right? One of the techniques we've learned before. This is why I asked you guys to please review and spend half an hour a week reviewing the older material, because we talked about these techniques previously, and now if you have it fresh in your mind, a problem like this becomes very, very easy for you to manage, right? Okay, so now that we have this, then what is the question we were asked? The zeros and the multiplicities, right? Okay, so if 3x plus 1 is equal to 0, then 3x is equal to negative 1, right? We're solving for x, so we need to isolate x. So move the positive 1 to the other side. It was positive, now it's negative. Then, is x isolated? No. We need to isolate it by getting rid of this 3. How do we get rid of the 3? We divide both sides by 3. So x equals minus 1/3. So that's the zero of the polynomial there, which I've highlighted. That's one of the zeros. What is the multiplicity of this? Multiplicity is 1. In fact, all these factors have multiplicity 1, right? So multiplicity is equal to 1. Does the graph cross the x-axis? What do you think? Yes, it does, right? Because multiplicity is odd in this case. So crosses x-axis, because multiplicity is odd. I'm running out of room here, as you can see, but I'll try to fit things here. So the second factor, x plus 4, set that equal to 0. So we have x equals minus 4, and the multiplicity is equal to 1, just 1.
And therefore, because this is odd, 1 is odd, so once again, the graph of that polynomial will cross the x-axis, crosses x-axis at -4 comma 0, which is the x-intercept. Okay. One more. I don't have any room here, but I have some room here. Let me, if you don't mind, I'm going to make a box here and write the rest of this solution here. So x minus 4 equals 0, x equals 4 is another 0 of the polynomial, of this polynomial. This has multiplicity equal to 1, right? So we know it will cross the x-axis. Okay? Okay, I hope this was easy to follow. Now let's go to the computer and plot all these polynomials. This one, this one, this one, this one, and this one. So 5 polynomials. And then because you're not going to, as I switch to the computer, you're not going to be able to see these notes. So I hope you took notes as we were doing this. Or if you haven't, you can rewind the video, take notes, because you want to have that information in front of you as you look at the graphs that I'm making on the computer. Okay. And by the way, please don't mind the glitch in your screen in the video as I switch to the computer screen. That's just switching from dock camera to the computer. It'll make that. Okay. All right. So we're back. The first polynomial was f of x equals x plus 5 to third power and times x minus 4 times x plus 1 squared. Okay. So I'm zoomed in too much. Let me zoom out. And I think we're in, let me make this in projection mode. And let me zoom out. Wow. So this polynomial is hard to see on this computer screen because as we zoom out, so let me zoom in onto zeros though. That's what we're interested in. Like that. So we determined that at x equals minus 5, let me zoom out maybe a little bit, like that. At x equals 5, negative 5, we have a 0, right? Right there. And I'm going to snap to it, negative 5 comma 0. Oops. Negative 5 comma 0. Right there. At that blue dot, we have a 0. Clearly, we have a 0 at that point, right? And again, I remind you that this technique that we just used on paper comes to us from centuries ago. So now, with technology, we can verify it, right? Look at that. And then, so we ended up deciding that the multiplicity of negative 5 was 3, which is odd multiplicity. So we expected the graph to cross the x-axis, and you can clearly see, reading the graph from left to right, read the graph from left to right, it's crossing the x-axis, right? So everything was true, was correct. Then the other x value or the 0 value is negative 1. Look at that. At negative 1, we clearly have, let me snap to it, at negative 1 comma 0, right there, we have another 0, right? We predicted that. And the multiplicity of that one was even, was 2. So we would expect the graph not to cross the x-axis. Look at that. Let me zoom in on it. So you can see that the graph did not cross the x-axis at that point. It just hits -1. Look at that. I'm now zoomed in so much so you can see it. See, the graph hits -1 and bounces back. Read it from left to right. So the graph is coming up from left, hits that point, and then bounces back to the same side because the multiplicity was even, was just 2. Okay? We can see that very nicely there. The other one was x equals 4. Let me zoom out so we can see that. Right there. Right there. And so that was 4, 0. And I'm going to snap to it with this right there. So the multiplicity of that one was odd, was 1, which is odd. So we would expect the graph to cross the x-axis. And look at that. It's clearly crossing the x-axis, right? But the nice one was this -1, 0, that one, where that one, that such that the line of the graph hit -1, 0 point and then bounced back to the same side. That was very interesting to see. Okay, so let's graph the other polynomials. The next polynomial was f of x equals x plus 1/2 and that was the, no power there. So that, and then times x plus 7 squared, like that, and then times x plus 5. And let me zoom out. So there. So here we had 3 zeros. One of them was at x equals -1/2. And it had odd multiplicity. Multiplicity was 1. So that's right there. Let me snap to it so it's more visible. Minus 1/2, 0. Right there. And let's zoom in on it. Right there. Do you see it? So the line is clearly crossing the x-axis. Let's zoom out and look at the other zeros. The other 0 we had for that problem was x equals -5. Look at that. Looking at the graph, we are sure that the multiplicity must have been odd, right? Because the graph passes right through -5, 0, right there. Let me snap to it with a point. Right there. And I'm going to label it like that. Right? We can zoom in on it a little bit like that. That one, this one. Okay? So the other 0 was -5. So, no, we have that. The other one was, -7. So let's snap to it, -7, 0, right? And label it right there. So looking at the graph, we are sure that the multiplicity must have been even, aren't we? We're sure. Because look at the graph. It hits the x-axis, reading it from left to right. It comes from left, it hits the x-axis, and then bounces back to the same side. It doesn't cross the x-axis to the other side. Okay? So we are sure that then the multiplicity of -7, 0, x equals -7 must have been even,
In fact, it was 2. Multiplicity of that was 2. Another subject, it's not in this section, but let me prepare you for the next section, which would be section 4.2. One of the things you should notice, and those of you who will be taking calculus for sure will be dealing with this a lot more than those of you who will not take calculus, but notice where the line crosses the x-axis. Do you see it at that point, at negative 5, 0? At that value, at that point, think about what happens to the value of the function. In other words, if we're reading from left to right, then reading this graph from left to right, we're coming towards this point from above, right? Above the x-axis, that is. What sign, let me not value, when I say what happens to the value of the function, I mean, let me rephrase that. What happens to the algebraic sign of the value of the function along this line, along this graph, before and after it hits the point, before and after it has this x-intercept? What happens to the algebraic sign? If we're up here, the algebraic sign of the value of the function, is it positive or negative? If we are above the x-axis, the value of the function must be positive, right? If we're below the x-axis, if we cross the x-axis at that point, if we're below the x-axis, anywhere on the line after the x-axis, below it that is, what is the value of the function? What is the algebraic sign of the value of the function? Is it positive or negative? It must be negative. So this is true for all zeros of a polynomial that have odd multiplicity. Because if they have odd multiplicity, that means the line will cross from one side to the other side, right? From one side, from positive to negative function value, right? Because if we're below the x-axis, the value of the function has to be negative. If we're above the x-axis, the value of the function has to be positive. And you can see it on the graph right here. Okay? Let's look at this one. And because we're reading the graph from left to right, so here, the line is coming from below, and then it hits the x-axis at that point, minus 1/2, 0, and then moves above the x-axis. So think about, as you look at that on the screen, think about what algebraic sign the function value has before and after it hits that point, that x-intercept. Before it hits it, it is negative, right? Because it's coming from below the x-axis. Once it hits the x-axis and crosses over to above the x-axis, then now the function value must be positive. That transition from negative to positive, or from positive to negative, for this one, for negative 5, 0, this point, the blue one. So this transition from negative to positive or positive to negative, depending on which side of the x-axis the line of the graph is approaching the x-axis, this is something that we will look at in the next section, 4.2, as the intermediate value theorem. In calculus has significant applications, but also in this class it comes up. It comes up in section 4.2. So when we get to that intermediate value theorem, I wanted to talk about it since we have the computer in front of us here on the screen, so that you have an idea. So you have an idea about what intermediate value theorem is, because section 4.2 describes it in words, and this gives you a visual reference as to what intermediate value theorem is. Intermediate value theorem basically says if you have the value of the function, if you have two values of x, right? Any two values of x. You evaluate the function, the polynomial in this case, at one x value, and you get a positive value for function. And then you evaluate at the other x value, and you get a negative function value. What does that mean? That means at some point between those two x values, there must be a zero of the function. Do you see that? Do you see how that makes sense? So if you're transitioning from positive to negative or negative to positive function value, then in the middle of those 2 points, there must be a zero of the polynomial. There must be a zero of the function, because that zero was the point or the x-intercept at which the transition took place, from positive to negative, from negative to positive. So just by looking at the function value, if you have opposite signs for two x values, then you know in the middle there must have been some place where the line went through the x-axis because it transitioned from positive to negative or negative to positive. And if you have two x values such that you evaluate the function value at those 2 points and they both have the same sign, either they're both negative or both positive, what does that mean? That means there is no x-intercept between those two, because the line of the function stayed on the same side, so it didn't transition from one side to the other. Okay, so that's intermediate value theorem. All right, so let's look at the graph of the other polynomial. It was f of x equals x squared minus 4 and all of that squared. Okay, so let's zoom out so we can better, see. Oh, look at that. Okay, so now we have, as we expected, we have two x-intercepts, right? These 2 points. And when we were solving this on paper, we figured out that one of these points, the left one, is negative 2 comma 0, right there. And let me snap to it with a label right there. And the other one, do you remember what was the other one? The other one was 2 comma 0, right? And that's the red one. So we learned, when we were doing this on paper, we learned that each of those zeros, negative 2 comma 0 and 2 comma 0, have multiplicity that is even. Multiplicity equals to 2, which was even. So we would expect the line not to cross the x-axis. Instead, we would expect the line of the polynomial to bounce back to the same side from which it is approaching the point. So we read the graph from left to right, right? So here, the line comes, hits that point, and then bounces back to the same side. And we would expect that because multiplicity of that 0 was 2, which is even. The same thing happens on this side. The line is coming from above, hits that point, bounces back to the same side. It doesn't cross the x-axis. So once again, we have multiplicity even. And we predicted all of this without even the technology at our disposal. Okay, so let's look at the other we have 2 more polynomials left to graph and look at. So the next one is x squared times x plus 3, again squared, times x minus 4 times x plus 1 to the 4th power. Look at that. Look at that. That's I mean, if I zoom out, I don't think, but that's pretty complicated, isn't it? Look at that. All right. So let me zoom in because we're interested on the zeros here. So we predicted that there were 4 zeros of the polynomial, and that's 1, 2, 3, 4. These are the 4 points. Let me snap to all of them so they're more visible. One of the zeros was 0, 0, or x equals 0. We calculated it. So 0, comma 0, right there, the green one. I'm going to snap to it. The other one was negative 3, comma 0, right there, the purple one. And, well, let me, because I want to talk about multiplicity too as we go through this. So the first one, 0, comma 0, right? Looking at the graph, we would definitely expect the multiplicity to have been even, right? Because let me zoom in, look at that. The graph coming from left, it hits it, bounces back to the same side, which is the negative side of the y-axis. So we would expect 0, comma 0 to have multiplicity even. And in fact, the factor was x squared. So it had multiplicity 2. So we predicted that, okay? That the line does not cross the x-axis. Negative 3, comma 0, let me move over a little bit. And if I think it was, oops, I think it was here, right there. See, again, looking at the graph, look at that. As I zoom in, you can clearly see that the line is hitting negative 3, comma 0 and bounces back to the same side, or the negative side of the y-axis, right? It bounces back to that side, below the x-axis. So we would expect the multiplicity to have been even, right? In fact, when I'm looking on my paper, the multiplicity was 2. So we predicted that the line does not cross the x-axis. Then, what else do we have? We have multiplicity or x equals 4. So where is that? Let's move over right there. See that line. Let me also snap to that one. So that one is 4, comma 0. Clearly, the line of the graph is going right through that point, right? Which means the multiplicity must have been odd. So let me see. Oh, multiplicity was 1. So we can see the evidence of that, right? It's going right through it. We have also another multiplicity, which was, which one did we not look at? Oh, negative 1. We didn't look at negative 1. So let me zoom in. Look at that. And I'm going to snap to it with a point. Negative 1, comma 0. The red dot that you see. Let's zoom in on it. Clearly, the line is not crossing the x-axis, right? It's connecting with it. It touches the x-axis at that point. At that point, negative 1, comma 0. But it bounces back to the same side, which is below the x-axis. So we know that the multiplicity for that 0, negative 1, comma 0, must have been even. And in fact, when I look on my paper, the multiplicity for negative 1, comma 0 was 4, right? Even multiplicity. So we would expect it to bounce back to the same side, and in fact, the graph did just that. Okay, so let's move to that last polynomial where we had to use factoring by grouping in order to find factors for. Remember that? The one that they didn't give us the factors for? Right? Sometimes these authors are mean and they don't give us all the factors, and we have to work hard to find those factors. But fortunately, we had a technique at our disposal that gave us the factors. Let me zoom. Oh, no. So something, sorry. One of these terms has to be cubed. That's the first one. So like that. And I need to zoom out. This looks like a complicated polynomial. Yeah. So it's so as I zoom out, I'm losing definition of the zeros, which are the x-intercepts. So let me zoom in, because that's what we want to investigate, the zeros of the polynomial. I think this would be good enough. Okay, so now we can clearly see all the zeros, all the three zeros of the polynomial, right? One of them was 4 comma 0. So 4 comma 0, right there, the green point that you see there. Maybe I can zoom in a little more. Barely, right? You can see it on the far right side of your screen. So the line, notice the line is going right through the point and crossing the x-axis, right? So we can say with certainty that the multiplicity of 4 comma 0 must have been odd. When I look at the factor, it was 1. In fact, all of these zeros had multiplicity 1, which is odd, so look at what is happening. At each of these zeros, and I'm going to snap to all of them, the other one was minus 1/3 comma 0. Right there, that one in the middle, and the one on the left was negative 4 comma 0. Right there. So at each of these three x-intercepts, or otherwise known as the zeros of the polynomial, the line is going right through the x-axis. So the multiplicity must have been odd, which in fact it was 1. Okay? Okay, so that's all the 5 polynomials that we worked on paper, and I hope that this was helpful for you to be able to connect what we discussed on paper to visually to all these graphs that we looked at. So let me switch back to the dock camera. As I do that, please don't mind the glitch in your screen. And when this happens, we spend maybe about 10-15 minutes on the computer, so please don't go away. I know your screen is blank right now because the dock camera went off. When we spend so much time on the computer, the dock camera saves power by shutting down, and now it's coming back up again. So please stay with me until the technology catches up with us. There it is again. Okay, so let me zoom in. Okay, we're back on track. All right, so here it says the next set of problems or examples, and I'm looking for my pens here. It says determine which statement is true or false, given what we've discussed so far. So polynomial x, or p of x, is that we are given this polynomial in factored form. It says then the graph of the polynomial function crosses the x-axis at 3 comma 0. What do you think? Is that true or false? If you want, you can pause the video and write down your own answers for all these three. There is another fourth one, part D. I can't put all of them on the screen, but A, B, C, you might want to pause the video, write down your answers, and then come back to the video. With everything that we've discussed, you should be able to answer these with no trouble whatsoever. Okay? Okay, I'm assuming you've done that. Now you've unpaused the video and you're ready to see how I answered these questions. And I hope our answers agree. So because 3 comma 0 is coming from this factor, and that factor has, that factor has power 4, which means that 0 has multiplicity even, right?
So it could not have, the graph of the polynomial could not have crossed the x-axis at this point, because this point, this 0 has multiplicity even. So the graph is supposed to touch the x-axis and bounce back to the same side, not cross it. So this is, they said, determine if it's true or false. False. False because 3, 0 has even multiplicity equals to 4. Okay? The next one. I hope that matches your answer. This polynomial, factored in this form, crosses the x-axis at 1/4, 0. What do you think? Well, 1/4, 0 must have come from this factor, right? So then, what is the power of that factor? 5, which is odd. So this is true. True because 1/4, 0 has odd multiplicity. Equals to 5. Okay? So it's odd, and the graph, as we saw on the computer screen, does go through the x-axis. Okay? So this one, if we are given this polynomial, then the graph of the polynomial is tangent. Tangent is the same thing as touching it but not crossing it. So let me write this down. Means, tangent means the line touches the x-axis but does not cross it. So I'll just give the definition of it. Does not cross it. Okay? So in other words, they're saying that this 0, -5, 0, must have even multiplicity. So -5, 0 must have come from this factor, right? Which has what power? 6. 6 is even. So it's true. It is true. The line must be tangent to the x-axis, meaning it must touch the x-axis, but does not cross it. So this is again true. Okay? How about the last one? The polynomial has these factors. Look at the factors. They both have even powers. So then the graph of the polynomial is tangent to the x-axis. Yes, so 4, well, let's see. Well, this is false actually. Do you see why? Why is this statement false? Do you see why that is false? Well, because if this is the factor, x plus 4 equals 0, then x must be -4. Then the 0 of this polynomial is not 4, 0, it's -4, 0. So -4, 0 is not equal to 4, 0. 4, 0 is not a 0 of this polynomial at all. So it has no multiplicity. So it doesn't, the graph, even if it goes through that, well, let's see. The graph of this line does not go through that point, period. This point is off somewhere on the screen. It doesn't match. So we can say false. Okay? Simply because this point doesn't belong to this polynomial. That's all. I mean, we can quickly, if you don't mind, we can quickly switch back to the computer and plot this point and plot this polynomial. They're going to be off. So they're not connected at all. So please don't mind the glitch in the screen as I switch to the computer. Okay, we're back again here. And I will do this quickly so the dock camera doesn't go off. But we're almost at the end of this section anyway. So
let's look at that polynomial. It is equals x plus 4 squared times x minus 1 squared, right? That's the polynomial. Then the point 4 comma 0, oops, let me, 4 comma 0, look at that, it's way off. It's right there. Do you see on the far right side of your screen? Let me go to projection mode. Oops, no, we were on the right track. So if I zoom out, the red graph shows you the polynomial, but the blue dot right there shows where the 4 comma 0 is. The line, the polynomial, doesn't even go through that point. So that's why that statement was false. So we're almost wrapped up with this section, but there's a couple of topics that I want to talk about, not only because these appear on your homework for this section, but also if you understand this topic, you really get a good understanding of polynomials in general. So it has a conceptual facet to it that helps you understand not just calculation part, but also the big picture. How polynomials behave in general, it's very, very important. So one of those topics is called using the end behavior So using the end behavior diagram to describe the end behavior of a given function. So that's one thing I want to talk about. The other one is called using the leading term. We've already talked about the leading term, right? So using the leading term, let's see. Using the leading term test to match the function with its graph. Okay, very, very interesting topic, these two, that I hope that it makes it easier for you to understand functions in general, not only functions, but also polynomials in general. Okay, so let's talk about this one first. So that, let's number them, and let's talk about the first one. So we're going to talk about number 1, using the end behavior diagram. The end behavior of a function. So there is a pattern in the way particular functions behave. So for example, if we have a quadratic function, let's start with the basic quadratic function. Let me move this up a little bit. So if this is x and y, so if you have the graph of a basic quadratic function, which goes through the origin like that, and this is, let's call this f of x equals x squared, notice how the end point of this function is behaving.
the end points. We're talking about the end points. Not in the middle, not over here, but the end points, right? So if you then have another function with even power, so if you have, suppose if you have, let's say, x to the sixth power, right? Another x or another power function with an even power, then the graph will retain its general form as far as the way these end portions of the graph behave. So, in other words, the other parts of it, it's going to look like this. So if you have, you're going to have this kind of behavior at the bottom. At the bottom, it's going to flatten out a bit. Compare that with this. Well, it should go through the origin actually. Let me correct this and say, well, let's keep this and say f of x is equal to x to the sixth plus 1, right? So that would match that. But now notice the end behavior of this graph. It retained its general feature. Okay, it retained its general feature. So the same way, if we go to, say, a higher power, as long as it's even, let's say f of x equals x to the 10th power, right? So again, we will have and pay attention to the end behavior, how the end is behaving. Almost like a fork, right? Like that. So the end behavior stays the same. Why is that? Because this power function, the powers are all even. So 2, notice the power, 2, 6, and, I haven't written down this one yet, but say f of x equals x to the 8th power, right? So notice that these powers are all even. So what happens? So that's what we basically expect to see. If you have even powers of x, you would expect to see this kind of behavior. So if you have, the general feature that we're seeing here is this kind of behavior, right? For even powers. And let me attract your attention to something else. Notice the coefficients of these functions, it's all positive. So they're all pointing upward. This end behavior is always pointing upward, right? In the same direction. And they all have this kind of feature. Arrows pointing like that, upward, for all these three functions. Now what happens if we take these and put a minus in front of them? What happens then? Well, they flip upside down and they reflect themselves across the x-axis. So this is what I mean. So suppose we do that with this guy, with this one, right? Let me move this down a little bit. So if we say, graph, let's say f of x equals minus x squared, right? Then the graph is going to flip. The same graph is going to flip upside down like that. Notice the end behavior once again. It retains the same shape, but it's flipped upside down, only because we have a minus in front here. Okay? But the power is, of course, even again. So if we do that with the other graph, with x to the 6th power plus 1, it'll look like this. it will look like something like this, like that, and like that. And this would be f of x equals minus x to the sixth, and then we want move down, so it'll be let's say minus 1. Okay, it'll be minus 1, not plus 1. And what happens with this one? The same way. If we have a minus in front, notice here, once again, I should actually color these in a different color. Let's say red, like here and there. So that's the significance, the significant difference between these three graphs and those three graphs, with the minus in front of the x here. And then, so let's do the same thing here. And we get something like that. And this would be f of x equals minus x to the 8th power. Right? So now the powers stayed even like that, but we have a minus in front of the power function there, and so they flip. But again, the end behavior of this diagram, notice the pattern. And I'm going to thicken this line so you can see for the above three functions, the pattern is upward, right? Two lines like that pointing upward. But for these three, the pattern would be down like that, right? For all of these, the end behavior is like that. By the same token, you can say the same things about the cubic function. So let's look at that, some examples of that. For the cubic function, let's start with the basic cubic function. All right. So we have, if we have f of x equals x cubed, let's start with that, the easiest one. The graph is going to look like this. Okay, like that. Notice the end behavior. One is pointing down, the other one is pointing up that way, right? And the whole thing is going through the origin. What happens if we look at the graph of another function that it has a power, say x to 7th power, and we keep the coefficient positive? So what happens then? Well, once again, it's gonna be steeper than that. It's probably gonna go like this. A computer would do a much better job than me if we graph these on a computer, but you're gonna have this same scenario again because the power stays odd. Notice the powers are odd, right? But this is a higher power. So this is going to be a steeper graph than that one. Okay, so, and we will have, actually there will be a flattening. There will be a flattening here of that too. So something like that. But once again, the middle, it's gonna be different than this. But the end behavior, notice the end behavior stays the same. This one is pointing up on that side, this one is pointing down, the same thing happens for this one. If you increase this power and or even x to 5th power or x to, say, 9th power, or any other odd number, the end behavior doesn't change. So it's still we're going to have something like this. So let's say f of x equals x to the 9th power. Notice the end behavior stayed the same. One side points down, the other side points up, right? And this is the kind of pattern we would expect whenever you have odd power, 3, 7, and 9. Okay? What happens, like the other set of examples, if we put a minus in front of these? Well, the same thing, but it's flipped across the y-axis. So let's see how would that look. So if you have this, let's draw all of them here. Like that. And this was also x and y. So we're going to graph these three functions, minus, as opposed to x cubed, minus x cubed, minus x to the 7th, and minus x to the 9th power, right? So again, I should have done this with a different color, so to help it stand out like that, okay? So what happens to the graph? Well, the graph flips the other way, like that, and like that, and like this. Okay? Notice the end behavior, though, didn't really change. I mean, one side points up, the other side points down. So the end points always point in the opposite direction. The same way here, the same way here, same way here, same way here. Okay? So when you have a power function or a polynomial with the leading term with having odd power like this, then you would expect this kind of behavior at end points of the graph of that power function or polynomial. So in other words, if we generalize this, then you're either going to have, with odd powers, you're either going to have this kind of behavior, right? Or this kind of behavior, when you have a minus in front, like that, and like that, okay? So compare that with the even powers, like that. They both point in the same direction, either up if the coefficients are positive, or down if the coefficients are negative. Okay? And that's with the odd ones. All right, so let's see how this kind of helps us predict how the end behavior of a polynomial will be given these kind of rules. So here's an example. So suppose we have this function, right? We have f of x equals minus square root of 3x cubed plus 4x squared minus 2x plus 4, right? So, and if I say A, B, if I give you a multiple choice question like this, right? And if I say how do you expect this function, the end behavior of the graph of this function will be? Will it be like this? Will it be like this? Will it be like that? Or will it be like this? Okay? So what would you say? Would you say, how would you determine that? How would you determine which one of these is the answer, would be the end behavior of the graph of that function? Well, if you said, look at the leading term, you'd be absolutely correct. This is the leading term, right? This term is a leading term. Why? Because it's got the highest power. So that is the leading term. And it's, what's the power? Is it even or odd? It's definitely odd, right? So we would expect either this kind of behavior or this kind of behavior, right? So which one do you think this is? So for sure we know that A and C are out of the question. Because the leading term's power is odd, we would either expect to see either this kind of behavior or this kind of behavior. In other words, the end behavior is in the opposite direction. One is going up, the other one is pointing downward. So it can't be A or C, because A and C, the end behavior, both sides are pointing in the same direction, either down or up. So it's either B or D for this function, the end behavior, right? But which one? Well, notice the coefficient is negative. When the coefficient is negative, what did we say? We said that the left side, it's going to point up, the right side is going to point down. Left side up, right side down. So which one is that? Which one of these is that? That's for sure B, right? It's this one. So I should have actually completed that question. Suppose we have this, choose the correct end behavior of the graph of the function. Okay? And we did. It's B. This one. Okay? All right, so let's do another one. Another example like this. Suppose we have, here's another example. Suppose we have P of x equals minus pi x to the 6th plus x to the 5th minus x to the 4th minus x plus 1, right? Looks pretty complex at first sight, but which one is the leading term? The leading term is the term with the highest power, right? In this case, it would be this one. It has the highest power there. So this is the leading term. Okay, so the leading term has the highest power that is even. So that means we would expect, let me bring this slide back. We would expect this kind of behavior where the end behavior is pointing in the same direction, either up or down, both ends, right? Okay, so then in that case, which one is this? Are they pointing up or down? As you think about that, let me list the answers for this. So suppose we have that. Choose the appropriate end behavior of the graph of this function. Okay, so let's say A, and I'll just list 4 answers, B, C, and D. Let's say A is doing that, this kind of behavior for the end part of the graph. B, let's say it's going like that, downward. And let's say C is this kind of behavior, and let's say D is this kind of behavior. Right? Okay. So we already decided that the leading term's power is even. So it's either going to be A or B, right? Definitely not C or D, because C or D would be associated with an odd power, like 7, 9, 3, something like that. Right? So it's either A or B, but which one? Is it A or B? Well, if you said B, you're absolutely correct. Because in this case, let's see, so in this case, the coefficient of the leading term is negative. So it's flipped upside down, so it would be this one. It would have to be this behavior. Okay, so it will be that one. Okay. Let's do another example. This one is interesting because it's kind of, at first, it's kind of misleading, but it again is not. So let's suppose we have this function, f of x equals minus 4.1 x to the 4th plus x to the 6th plus 0.5 x to the 7th. Okay? Choose the correct end behavior for the graph of this function. Okay, and let's list the answers. So we say A, B, C, and D. So let's say A is looking like this, B is looking like this, right? Arrows pointing in the opposite direction. C, let's say it's doing that. Arrows are pointing in the same direction again. And D, the endpoints are doing that, pointing in the opposite direction again. So what do you think? Which one of these would be the end behavior for the graph of that function or polynomial? Well, this one is interesting because the first term is not the leading term, right? They decided to, whoever designed this question, and it's not me, this is part of your book, decided to put the leading term not first, but at the end, right? This term has the highest power, so this is the leading term. So our leading term this time, we got to be careful, happens at the very end, right? So this is the leading term. Like that. And the leading term has a power that is odd. So we would expect the end behavior to be arrows that point in the opposite direction, right? So that means A and C are out of the question because A, the arrows are pointing in the same direction downward. C, arrows are pointing upward in the same direction. So it's either B or D. Either B or D. So which one? What do you think? Well, we learned that in the previous slide, we learned that if the coefficient is positive, if the coefficient of the leading term with odd power is positive, then the left arrow or the left end is pointing downward and the right end is pointing up. Left side is pointing down, right side pointing up, right? But if the leading coefficient has a negative in front, if the leading term has a negative coefficient in front, then the left side or the left end is pointing up and the right side or the right end is pointing down, right? So we definitely have the leading term has a positive coefficient, right? So between B and D, with positive coefficients, the left end is pointing down and the right end is pointing up. And that would be D, right? So it's this one. Okay, so this would be our choice. So this is the concept of end behavior of a diagram. Okay, so the next thing we want to talk about, let me organize this stuff, is the concept of the leading term test. So at the beginning of this section, we talked about leading coefficient, leading term, and so on, and the degree of a polynomial. It's nice to know what they're used for. So this is the case 2. And it's about using the leading term test to match the function with its graph. Okay? So how does this work? Pretty much based on the same principle, but this time we're not matching the endpoints, we're matching the entire graph. Okay? But it's based on the same principle. So let's see some examples right away, right? So suppose we have this function minus x to the 6th plus 2x to the 5th power minus 3x squared, right? And these are the 4 graphs that we're given. Suppose we have this. Choose the correct graph below. Okay? So let's say, so we have 4 of these. 1, 2, 3, and 4. So these are x axes, and of course the y like that. And here are the graphs for each one. One looks like that. One looks like this. Right? Notice already you see the pattern, right? This one, the ends are pointing in the opposite. This, the ends are pointing in the same direction. This next one, once again, the arrow or the end points are pointing upward. And again, this one, the end points are pointing in the opposite direction. Okay? So let's call this A, B, C, or D. So which one would you choose, right? Well, once again, notice the leading term. Let's scan all three terms. The highest power is this one. So this is the leading term, right? Now, the leading term has an even power. The even power means that the arrows must point, at the end must point in the same direction, either up or down. But which one is this? Is it going to be upward or downward? Well, so we know right away, first of all, because this is even, we know A and D are out of the question because the arrows are pointing in the opposite direction. So either it's B or C, right? Because this power is even. So, but which one? Is it this one or this one? Well, we learned that if the coefficient in front, it's a minus, then it's a graph that is flipped upside down. So it has to be B. So the correct, because of that minus in front, it's this one. This is the correct graph for this one. Okay, it is B. I hope this is starting to make sense. So you see why you're not doing any calculation here, but everything is conceptual. So conceptual understanding is very important. It saves us time, and it gives us a better understanding about how power functions like this behave. There's a pattern that the way that these power functions or polynomials behave, right? Okay, so let's see another example. Suppose we have this function. So let's say match this function f of x equals x to the fifth plus 1 over 5 x minus 6. Match this function with its graph below, with the correct graph below. And I'm going to list the graphs with the correct graph below, right? So here are the 4 graphs again. So we have x, x, and x, and of course the y-axis. Right, like that. So one graph looks like this. Right? The endpoints are pointing in the same direction. As I'm doing this, you got to be thinking now about the leading term and what the graph should look like, right? You should have a good understanding of how this graph should look like. Okay, and let's call this A, B, C, and D. Okay, so given this function, which one of these graphs would match it? Well, the first thing it should catch your attention is the leading term, right? That's the leading term, the term with the highest power. So this is our leading term. And the power is odd this time. It means that the endpoints should point in the opposite direction. That means right away that A and D are out of the question, right? So either it's B or it's C. Well, which one is it? That's when we look at the coefficient of the leading term. If it's negative, it would be this one. If it's positive, it would be that one. So it's positive, so we know it's got to be B. Okay, so that's the correct match. That function matches that graph. All right, so let's do another example before we wrap up this discussion. So suppose we have this function. Right? And suppose we have that. And we want to match the function with the correct graph below. Okay, and here are again 4 possible answers. Like that. All right, so let's call these A and B and C and D. Okay, so again, the first thing that should catch your attention is the leading term. Clearly, that x to the 6, that's the leading term, right? It's the term with the highest power. And the power is even. So we would expect both endpoints to point in the same direction. That means B and D are out of the question. So it's either A or C. But which one? Well, we learned that if the coefficient is negative, the graph is going to be upside down. But the coefficient is positive, so it's going to have to be C. Okay, so it is this graph. Notice how powerful and useful this method is. You don't have to do any calculations, but when given several options for a graph, you know exactly which one to pick. and that's just the connection between the leading term and the way the end point of a graph is going to look. Okay, so I hope that this discussion was useful. As usual, I want to thank you for persisting through these videos. Rewatch these if you have to. That's quite normal, and videos in that sense are useful. So don't think that that's something that it means that you're not good at this stuff. No, a lot of times it's quite common that we have to watch these again and again in order for this stuff to sink in. So thank you for joining me in this video again. Have a nice day for now, and I'll see you again next time.